Hello, my name is Michael Bartz from the German Research Center for Artificial Intelligence, and this talk is about our 2020 ETRA paper called Visual Search Target Inference in Natural Interaction Settings with Machine Learning. I'm happy to present this work at this year's virtual conference. Let's start with a short definition of the term visual search. It depicts the process of detecting a target visual stimulus among distractor stimuli. In complex visual search scenarios, methods for predicting the search target can help to construct and improve intelligent user interfaces. The idea is that using eye tracking and the fixated visual stimuli as input, we can automatically recognize what the user is looking for. This information can be used to adapt the interaction or to support the user proactively. In this example, the system might detect that the user is looking for red cars, and it could highlight available instances to accelerate its search process. Related research investigated several approaches to search target inference. For instance, Borgi and colleagues investigated algorithmic principles using generated dot-like patterns. They asked users to find a displayed subpattern in a large pattern. Satar and colleagues presented a method for predicting the class of a search target. They asked users to find a displayed book cover in a collage of 84 books. They encoded the scan path using the back of visual words algorithm. Similarly, Stauden and colleagues presented an encoding based on activations of a pre-trained CNN, a convolutional neural network. Their encoding method is called back of deep visual words. We used this method as a baseline. Satar and colleagues also presented a method for predicting the category or attribute of potential search targets. For this, they asked users to find objects of a certain category or with a certain attribute in an image collage of 20 pieces. However, related works are constrained to artificial data sources with a specific format, like the dot-like patterns, or image collages with clearly defined object boundaries and a limited set of target classes. In addition, they suffer from low prediction performance. In this work, we contribute in three ways. First, we propose to predict the segment class that contains the search target instead of directly estimating the object class of the search target. For this, we replace the prediction label with the corresponding segment class. At first sight, this might be a disadvantage, because the target area cannot be inferred with the same spatial precision. However, we expect that this approach can be used with a great variety of natural scenes. The hypothesis is that spatial precision is traded off against better generalizability and better performance. Second, we propose a new encoding for fixation sequences. We generate a histogram of segment classes that are fixated during visual search. Sequence encoding is a necessary step to enable model training. We use SVM models for this purpose. Third, we manually extend the view dataset such that it can be used for model training and testing. In total, we compare three different encodings: the back of deep visual words encoding from Stauden and colleagues, or novel encoding, the histogram of fixated segment classes, or in short, HOFIS, and a concatenation of both feature vectors. We use each encoding method for training and testing a predictive model that infers a target segment Y. We use an extended version of the view dataset for training and testing our methods. It includes scan path from visual search trials from 19 participants. We extended it by manually annotating each image with a target area using bounding boxes, and we used SegNet for automatic segmentation of all images. The target segment and the segment-based encoding can be extracted from this. Finally, we selected 8 segment classes that occurred at least 21 times to get a balanced dataset. You can download this dataset from GitHub. Next, we present the results based on this dataset. Here you can see the model accuracy when training across users. We train an SVM model using a twofold cross-validation in which we leave half of the users out in each iteration. The back of deep visual words encoding achieves an accuracy up to 17%, depending on the used CNN layer. The combined encoding is much better, with an accuracy up to 46%. Models trained with our novel encoding achieve the best score overall with 52% accuracy. We also trained user-specific models. Here we used a tenfold cross-validation per user. The back of deep visual words encoding yields a similar result of up to 18% accuracy. The combined encoding is also better with up to 43% accuracy. And our novel encoding alone is also the best overall with around 68% accuracy. With this work, we contributed to the field of search target inference in 3 ways. We proposed to predict the target segment instead of the target object. We implemented and tested a new encoding for fixation sequences. And we created and published a dataset which can be used to evaluate new search target inference methods. Thanks a lot for your attention.